Tracking tiny insects in cluttered natural environments using refinable recurrent neural networks. Given very challenging videos like this, we want to be able to track the insects throughout the full video. We propose a novel deep learning-based tracking framework capable of detecting tiny and visually camouflaged ants covering only a few pixels in complex and dynamic high-resolution videos. We introduce refinable recurrent hourglass networks, combining color and temporal information to continuously detect insects recorded using a freely moving camera. The architecture provides comprehensible heatmaps of positional estimations and an integration of optional user input to refine the tracking results. The resulting framework provides a foundation for challenging tiny single object tracking scenarios and a practical and interactive solution for biologists and ecologists. The architecture receives the RGB image as well as the motion maps denoted as M as its input. Motion maps are simply pairwise differences of successive images after rectifying camera motion using homographies. The method can be separated into three different modules, namely single frame module, recurrent module, and refine module. For the single frame detection, the pooled feature map output of the backbone is used to compute the position of the object directly. The recurrent module adds a temporal memory by appending an LSTM to the spatially pooled feature representations. The LSTM receives the current pooled backbone representation as its input and computes new spatial temporal representation. These representations are added to the pooled backbone output and the prediction is created analogously to the single frame module. During refinement, user input, for example a starting point or corrections, can be incorporated by replacing the LSTM's hidden state with a new version based on an MLP's representation of a user-provided location. These corrections can be propagated forward to the next frame or also in a bidirectional fashion to the previous frames. The hidden state is replaced and used for neighboring predictions as shown in the figure. The method is tested on a dataset consisting of over 100,000 frames from different videos recorded using a handheld camera with 60 FPS, and the proposed method outperforms other state-of-the-art algorithms on this challenging dataset. In our ablation study, we studied the influence of different input modalities, inference directions, and different backbones, and conclude that the motion maps are more important than RGB information, while their combination gives the best results. Moreover, recurrent inference greatly improves the performance, and as a backbone, hourglass performs best. While the refinement module does not improve the results substantially when observing the median, the mean is reduced considerably from 19 to under 9 pixels. In a qualitative analysis, you can clearly see that the single inference on the left is quite noisy with lots of outliers. Recurrent inference in the middle reduces outliers substantially, and remaining outliers can be removed by supplying user input. The easily interpretable heatmaps also support this. Heatmaps of single inference are very noisy, while heatmaps from the recurrent inference are much more focused on the actual insect. In conclusion, our solution outperforms two state-of-the-art algorithms on a challenging single insect dataset. The fast integration of manual corrections combined with a direct and interpretable feedback in form of heatmaps make our solution a valuable system for a variety of animal behavior studies. The framework was tested on an extremely challenging ant dataset, demonstrating that the hourglass networks with LSTMs outcompete all other tested methods. In the future, we want to use the heatmaps to guide a user to potential frames with high uncertainty for subsequent refinement. Moreover, we want to incorporate multiple object tracking into the framework.